We have a traveling wave, frequency omega, amplitude A, and the wave is traveling along a string of mass density mu. We want to address the question of energy in the wave. So what we do first is let's consider some position x on the string, doesn't matter what the position is, and an increment delta x about x. Now we enlarge that down here. Here's the position x. Here's an increment delta x with x somewhere within that interval. Okay? Now, that increment, as the wave passes, is going to, if the wave moves a little bit, that increment's going to be, right now that increment is actually up here on the wave. And let's go ahead. So there's the increment delta x. And up here is that portion of the string. So let's call this the corresponding portion of the wave. So that increment is actually displaced up to here at this instant. Now, if the wave moves a little further, that increment is going to be back down at the equilibrium position. If the wave moves a little further, so that let's say the valley here is at position x, then that increment is going to be down here. And then if the wave moves a little further, so that this point along the equilibrium axis is here, then the increment is just right here on the x-axis. If we move a little further, so this peak is here, well, then that increment is going to be up here. So that increment is going to be oscillating up and down in simple harmonic motion if this is a traveling harmonic wave. And let's make this a traveling harmonic wave. Of single frequency, which means that everything's going to be in simple harmonic motion. Okay, well, so now that increment undergoes simple harmonic motion with frequency omega. I mean, these peaks and valleys pass with frequency omega. Amplitude A, the amplitude of the wave, is how far that increment is going to displace. And mass, delta M. Now, I've written down what that mass is, but let's stop and think about it before you should pause, excuse me, without looking at that expression, and think about what the mass of the string within that increment ought to be. What's the mass of the increment? Delta M equals what? Well, here it is. It's mu delta x, mu being the mass density, mass per unit length in this case, multiplied by the length of that increment, which is delta x. So that the mass increment is mu delta x. Well, now, what's the maximum transverse velocity of the simple harmonic, of the point on the wave? Because that's going to be the maximum velocity of the simple harmonic motion of this increment. Well, the maximum transverse velocity of a simple harmonic motion, frequency omega, amplitude A, I'll write down briefly like y equals a sine of omega t, and there could be a phase angle there. That's your y, that's your transverse position. Your transverse velocity is a time derivative of that, which is omega a cosine of omega t. When the cosine of omega t is 0, that velocity is then just omega a. And that is your maximum velocity. But I said when the cosine is equal to 0. When the sine is equal to 0, the cosine is equal to 1, and that gives you your maximum magnitude of the transverse velocity of this point on the wave, telling you that what then is the maximum kinetic energy of this increment. Okay, you should think that through before you look anywhere else in the board, but you should have paused and thought that through. The maximum kinetic energy is 1/2 m times the maximum velocity squared. Well, here's your mass, mu delta x. Here's your maximum velocity, we square it. So here's your maximum kinetic energy, 1/2 mass times maximum velocity squared. Now, what's the total energy of that increment? Well, the total energy is the energy of its simple harmonic motion. And the simple harmonic motion has the property that when you're at the equilibrium position, your potential energy is zero, potential energy being measured relative to equilibrium, and your kinetic energy is equal to the maximum kinetic energy. Well, total energy is potential plus kinetic energy, and it's the same throughout the motion. The sum of the potential and kinetic energies is constant for simple harmonic motion, so that equals the maximum kinetic energy, which is just this. It's also equal to the maximum potential energy. When you're at the extreme point, you slow down to zero. All your energy is potential. Conservation of energy tells you that in the simple harmonic motion, your total energy doesn't change because there's no non-conservative force acting. Potential plus kinetic energy is going to be constant, so that's also equal to the maximum potential energy. Now, the whole point here is that you have this interplay between potential and kinetic energy within simple harmonic motion, but the total energy is always the same and is equal to whatever your maximum kinetic energy is, if you can calculate that easily, or your maximum potential energy, if you can calculate that easily. Well, we calculated the maximum kinetic energy. That's this expression. So that is the total energy of the increment.